And we're back with optimization with parameters. This is another presentation that comes after we have taken care of the nuts and bolts of calculus. We're trying to do a bit of a synthesis of the conceptual as well as the symbolic tools that we have at hand now. And we will do that in this presentation by deriving Snell's law from another physical principle, which is Fermat's principle. And interestingly enough, the method that needs to be used is optimization with parameters. So let's look at what we've got here. Again, as always, first let's just see why we may need parameters in optimization problems aside from this example. I mean, there's a general principle behind this, right? And you've seen my standard intro in which I talked to you about why we need parameters, and it may be a little bit long-winded, but I'm just trying to encourage you there because switching to working with parameters can be a challenge, but I keep trying to say, look, it's well worth it, and we're going to see it here also. We've also seen in the soda can design example that we might as well carry letters rather than 4-place decimals through a computation. It gives us a little bit less to write. For this presentation, we can say it's now time to look at parameters that actually stand for an unknown quantity. And so the question that we're going to answer is a physical question. It's the question, why does a ray of light change direction as it goes from air into water and vice versa? Basically, anytime a ray of light goes from one medium into another, it bends a little bit. The principle behind that is Fermat's principle, which we are going to use as the basis for our derivation, and that is a ray of light will travel from one point A to another point B via the path that minimizes the travel time. This is something that has been verified physically, and so the other thing that has been verified is that light travels faster in air than it travels in water, and that would mean that you would travel longer in air before you switch into the water to get actually to point A, to point B, which is under the waterline maybe, and that means it must change direction as it goes from one medium into the other, because if it travels longer in one than in the other, then the light ray no longer goes in a straight line from one point to the other. The phenomenon itself is called refraction. Refraction, you may have talked about it in physics class already. In fact, you may be familiar with Snell's law already. Well, here's a derivation of Snell's law from a more fundamental physical principle. So the question that remains really is, I mean, the physical principle says that the ray of light apparently is supposed to bend, but the question is, how much will the ray bend? And, well, that's where we just have to think about what the situation is, and we're going to see there's an awful lot of unknowns here. Namely, the velocity of light in air is v1, and the velocity of light in water is v2, and the way we're working out our derivation, it doesn't matter whether we're talking about air versus water, water versus air, air versus glass, glass versus water, and so on, because these velocities could be anything, right? So that's another advantage of working with parameters. The interface could be an interface between any two optical mediums that allow light to go through. Point A, well, what can we say about point A? It's at a height h1 above the water, that's about it. Point B is at a height h2 below the water, so we're talking still here about an air-water interface, but it could well be that this is an interface between two other media, and then we would say height h1 above the interface, height h2 below the interface. Sounds even fancier, sounds even more intimidating. That's why I tried to stay with air and water here, because the number of parameters we're dealing with here, it's bad enough already. The horizontal distance between points A and B, we don't know that either, so we call it D. The horizontal distance from point A to the point where the ray enters the water, which is the point that we don't really know, that distance is x. And the angle between the ray of light and the vertical line is θ1 above the water surface and θ2 below the water surface. So look at this. We've got 1, 2, 3, 4, 5, 6, 7, 8 unknown quantities here. That's certainly working with parameters. As far as I can tell, that seems like a complicated problem to me, and yet we will be able to get it done. The other thing that you see as I took stock of this situation here, this is of course very verbal. We're going to see it in just a second in the picture, but remember how I also often harp on us just needing to give names to the quantities before we do anything else. And here are all the names of the quantities that we have to deal with. So the task now is to determine under what circumstances the travel time from point A to point B is minimized. And so we do what we are typically doing when we are looking at something that has geometric content. We try to visualize it. Here is the interface, a horizontal water line, air up here, water down here. We've got a travel velocity v1 above the interface, a travel velocity v2 below the interface. We have a point A above the interface, we've got a point B below the interface. We've got a ray of light that somehow goes from point A to point B. That could also go this way, but in this picture we're apparently assuming that we're faster up here than we are down here, so we're trying to travel longer in the upper medium. Then we have a height h1 above the interface for the point A, a height h2 below the interface for the point B. We have a distance of, horizontal distance of d between the 2 points. We've got a horizontal distance of x from the point A to the point where the ray changes from one medium into the other. And, oops, what just came? Oh, there's another line that came in. And yes, now we are also talking about the angles. This angle here is theta 1. This angle here is theta 2. And by what we know from angles on parallel lines, that means that this angle here is theta 1 and that this angle down here is theta 2. So that is all the content that we had on the previous panel now encoded in a picture. And that's of course what we want to have. And this is of course why people rightly think that physicists are quite ingenious, because that's what these guys make a living with, right? They take a natural situation, they do an abstraction from that situation, and then they start setting up things like this with as many variables as needed, and then they start doing math on top of that. And that's what we're going to do now, because remember, the only thing that I ever will know about velocity is distance over time. Now what we want to analyze is time, and so we solve for t. We get that time is distance divided by velocity. And so now we can work out the travel time here. And the travel time, depending on where this point where we change from one medium into the other is, will be the distance traveled in the first medium divided by the velocity in the first medium. And the distance traveled in the first medium by Pythagoras' law is the hypotenuse of this triangle here. So by Pythagoras' law, that's the square root of x squared plus h1 squared, plus the travel time in the second medium, which is the distance traveled in the second medium divided by the velocity in the second medium. And by Pythagoras' law, with this length here being d minus x and this length here being h2, that distance is the square root of d minus x quantity squared plus h squared. Well, that's plenty bad. We've got a function with 1, 2, 3, 4, 5 unknown parameters. But remember, these things just act like constants, and that's of course how you handle parameters. You have to be a little bit cold-blooded here and realize those things are just numbers, so differentiation will not be a problem with those things. To minimize the travel time, to determine the x that minimizes the travel time, of course, we just have to minimize the function, and we can do that. We take the function, we rewrite it a little bit. I'm more comfortable with these constants being out front. That way I'm not tempted to try to use a quotient rule, which would also give the right result, but which would be overkill. And now we compute the derivative, and you can see, that is kind of nasty. That's the kind of stuff that you also sometimes see in a book. And then you wonder, well, how do we get from this line to this line? And well, how did we? We took the derivative. This is a constant, so the constant is copied down. Then we needed to take the derivative of this square root here. My marking, I apologize for the program, I have no control over that as far as I know. The marking didn't go too well, so we have to take the derivative of this square root. Well, the derivative of the square root function is 1 over 2 times the square root of the inside, so we get 1 over 2 times square root x squared plus h1 squared times the derivative of the inside, which is 2x, because remember h1 is a constant. Now, how did I get the derivative of the square root function? That's something you either remember because you run into the square root function that often, or you remember that square root of something is just that something to the 1/2, and the derivative of something to the 1/2 is 1/2 something to the -1/2 times the derivative of the inside. And so we've got the 1/2, and the square root in the denominator is the exponent -1/2. So that's how we got at least the first term here. And, well, how do we get the second term? Again, we've got a constant that we just copy down. The derivative of the square root is 1/2 times the square root of whatever is inside, times the derivative of the inside. The derivative of h2 squared is 0 because that's a constant. The derivative of d minus x squared is 2 times whatever is inside, which is d minus x, times the derivative of the inside, which is -1. So all terms are accounted for here. We can cancel a few things. We can cancel those 2's. We can combine the fractions again. We end up with x over v1 times root x squared plus h1 squared minus, and here we've canceled the 2's and just combined a few things. The -1 becomes the minus sign here. So we end up with minus d minus x over v2 square root d minus x quantity squared plus h2 squared. And that's what we have to set equal to 0 and solve. And that gets us this, right? I just brought the negative term over to this side and wrote things down again. And here's where you ask yourself, how are we going to solve this for x? And, well, that would not be pretty. But I think we could do it because after we square everything, we're rid of the square roots. And, well, no, that's what I also thought when I made up those slides. When you square everything to get rid of the square roots, then you still have to multiply things across. You end up with 4th powers for x. And so that would be hard to solve symbolically. It would still be possible because there is such a thing as the quartic formula. I'm not sure if it's called the quartic formula, but you can find zeros of 4th order polynomials. But the ingenious thing now that physicists, probably after looking at this for quite a while, realized is that this is an equation that must be valid for the minimum travel time. And it will indeed be the minimum travel time because if there is only one critical point, that critical point is either a maximum or a minimum. And if you push x way out, you get huge travel times either way. So it's got to be a minimum. So this equation is what the minimum travel, but the parameter for the minimum travel time has to satisfy. And then we're not really that interested in the x. We're interested in that angle, right? And we realize that the sine of θ1 is opposite over hypotenuse, which is x over square root x squared plus h1 squared, which is right here. And the sine of θ2 is opposite over adjacent, which is d minus x over square root d minus x quantity squared plus h2 squared. Now that is something that I was able to disclose fairly quickly here, and here's the equation. This is something that the gentleman Snell probably took quite a while to figure out, because you look at something like this, and it doesn't matter how much experience you have with that at first, you probably will be stumped, and I was too. There is no need to be self-conscious about something like that. When a problem is hard, it just takes a little bit more time. But ultimately, and this is really this wonderful capability that people in the applied sciences try to hone to perfection, is that you see these simple combinations, you find ways to combine them into something that is easier to read, which is this sine θ1 over v1 divided by equal to sine θ2 over v2. And if we now bring the sines to one side and the velocities to the other side, we're ending up with sine θ1 over sine θ2 being v1 over v2. And, well, that is Snell's law. Now, because in our derivation we never used that one medium was air and the other one was water, we can actually say the following. When a ray of light, A, leaves a medium in which the speed of light is v1 and enters a medium in which the speed of light is v2, then the angles of the ray of light against the vertical line at the point of entry satisfy sine θ1 over sine θ2 equals v1 over v2. And θ1 is the angle of the ray of light in the first medium against the vertical line, and θ2 is the angle of the ray of light in the second medium against a vertical line. So that is now a very nice physical law. I think the original form talks about the refraction index of the media, not so much about the velocities. So this derivation probably is not quite historically accurate, but nonetheless, this is an example where a fundamental physical law can be derived from more fundamental principles even. and it is called Snell's law of refraction. Final comments here. Well, we've used parameters here to analyze a very general situation, and what we've obtained is a law that applies to arbitrary rays of light and arbitrary media. So we've really derived a general natural law, which is kind of cool. And that's why working with parameters is so powerful, right? With parameters, we did not simply solve one example of one ray of light that goes from one medium to another, where one point is above a certain height above the waterline and the other one is a certain height below the waterline. We've done this for everything. This works in general, any medium, any configuration. So we obtain results that apply in many situations. And of course, that means we have to work a little bit harder and sometimes maybe even desperately look for ways to simplify the result. That changing that quotient from a quotient to signs, that certainly is the mathematical equivalent of a double backward flip just to get out of a tough situation, but we got it done, right? Now this is something that if you can do that repeatedly and reliably, then you will be a very good physicist, a very good scientist, very good engineer, very good mathematician, or whatever else your calling may be. But certainly I should acknowledge this is a very much a high-end situation, right? And yeah, the interaction of the angles was that double backward flip. But ultimately we also have to realize the purpose of calculus is not to pass a class. Now, don't get me wrong, I don't have a problem with you passing the class. In fact, I want you to make an A. There's nothing wrong with that. In fact, it's kind of enjoyable. It gives you an even bigger sense of accomplishment than the one that you should derive from simply passing the class. But nonetheless, if we're looking at the giants who invented calculus, who are Sir Isaac Newton of Great Britain and Gottfried Wilhelm Leibniz of Germany, they were entirely unworried about classes when each of them discovered calculus. Newton at that point in time was worried about the plague that was in London, because he was actually pretty much evacuating himself to his childhood home and was doing physics there as the plague was ravaging London and everybody just tried to not get infected. Leibniz was someone who pretty much did mathematics for a living, and he did these kinds of things to keep himself employed. So they were not unworried about classes, but they were certainly still worried about things that we would consider real life, or something like an equivalent of passing classes. But at the same time, they were very much interested in understanding nature, definitely because Newton was mostly acknowledged as a physicist, even though we mathematicians like to claim him too. Leibniz was very much interested in geometry, so there was a certain pursuit of wanting to understand nature, and that is really why we do calculus. We do calculus to understand nature. We do calculus because it is applicable. That's also the reason why in your science curriculum, in your engineering curriculum, you are required to take a long sequence of classes that prepares you for these kinds of things. If it was just a matter of calculus being a singular achievement of humanity that we just want to be aware of, then you would just have to take one class called Calculus Appreciation. There's nothing wrong with appreciating calculus. That's another goal of these presentations, to get you to appreciate this stuff. But in the end, you're going to use this to build better devices, to figure out nature. Get to it.